How many of you have seen my talk before? No one. One. Okay, good. Then I won't feel bad for... Actually, this talk has some new material. So if you saw my talk at the Beam Summit Berlin, there is new material in this talk toward the end, so you should definitely pay attention. I know I'm the last thing between you and dinner, so I'll try to go fast, but I expect it to take about an hour and a half to 2 hours. So, actually not. I'll go over really quick what SQL is, just to make sure we're all on the same page. I think you know what SQL is. And then I'll do a demo. It's not going to be as good as the demo last time. That was really amazing. You should actually go watch the video of the previous talk just for that demo that Pablo gave. It's great. I'll go into more of a technical deep dive on Beam SQL. And this is where there's some new material. I added a slide to explain what the new Zeta SQL stuff is exactly. And then I'll give a little bit of a roadmap of some of the things we're thinking about, working on. And then questions. You can ask me all the questions you want. And I probably won't be able to answer them, but I'll try. So, who here has used SQL before? Okay, a lot more hands up this time. Yeah, pretty much everyone has used SQL, at least in this audience. It's a tool used by data analysts, data engineers, ops people. It's an easy way to query large data sets and get useful results out of them. So, if you haven't seen SQL before, and I think almost everyone raised their hand, this should look familiar to you then. It's a pretty simple SQL statement. You're just, selecting the sum of foo. Maybe in your window, you've got some function, some condition you want to apply to it. Maybe some other filters that you want to apply. So it's all pretty straightforward. Really, if you have this, if you've seen this graph before, this is pretty much what our SQL pipelines look like. Also turns out to be what a Beam pipeline looks like. So they're a pretty good fit. So sort of our key characteristics of Beam SQL, that why would you want to use Beam and SQL, is we've got a wide-to-wide SQL engine. So we have all the advantages of Beam, right? If you have a large data set, we can scale up. Whatever runner you're using handles that. Beam has no built-in storage. So this is one of the sort of interesting things about our SQL is you're going to have to hook up your data sources. We have a CLI that makes that pretty easy to connect to external storage using Beam IOs. And we support quite a few. There's a nice list here. But the real key differentiator of Beam SQL is the streaming SQL support. And so part of that is where is your data in time? You've got to process this data that's not at rest. So now you have to break it up into chunks that you can actually process. And so we've added some extensions, tumble, hop, session, operators that you can pass into a group by to break your data up into chunks that can actually be processed and have a result happen on a stream. So you can do aggregates on streaming data using these concepts. There's actually a talk tomorrow, 1 p.m. One SQL to rule them all. I think Julian Hyde and Ken are here. They're going to give that talk to actually explain some of these operators and where we're going with them. But you should definitely attend if you're interested in that. One other thing to note is there's this window over concept in the SQL standard, and that's not something we support. I've gotten asked about that a couple times. If you're familiar with like time series SQL, that's pretty common there. And then I just want to shout out to all the Beam SQL contributors. There's a lot of them. I probably missed some people up here, but it's a pretty large group. working on SQL now. I would say this is like, I don't know, quarter of Beam maybe? Okay, that's probably overly optimistic. So the next thing I'm going to demo here is a quick demo of the Beam SQL CLI. Has anyone played with Beam SQL before? One. Okay, so I'm pretty sure Ken has. So pretty straightforward. Let me get out my handy dandy shell here. So I got this jar that I happen to grab off Maven Central. It's just from the Beam 2.15 release that just came out recently, but these actually are available for a while. If you download the jar, you can just run it with Java jar. Next thing you know, you have a SQL shell. It's pretty amazing. So no need to go and even pull out your Java source code and compile. There's artifacts there on the internet that you can use. And so I'm going to start with a pretty simple example here. I'm going to do a create external table. Times that. So we have a sequence generator that Pablo added for so what I'm doing here is I'm creating a table. I'm not actually creating the physical data structure, but I'm creating a pointer to an external data source. In this case, the external data source is actually a piece of Java code that generates sequences for testing, and that's the type sequence. And then the data here, the actual types describe the schema of that table. So I run this. Great, I've got a table. And I can do something like So I can select 10 records out of that sequence generator. And it will spin up a Beam pipeline in the direct runner and give me out some data. So all the sequence generator does is give you a set of increasing integers and some timestamps. It's a good tool for writing demos, playing around, seeing what you can do with SQL without actually connecting to external resources. So that's why I'm using it for this demo. Didn't want to tempt the demo gods by trying to connect to PubSub, and because the Wi-Fi here is not super reliable. So if I want to do something more advanced, select count star, dumble start. So this is the windowing.
Tumble there, I think.
Uh-oh. I'm already having syntax
That
errors.
could be something I don't know about, but tumbling over data.
Okay, so what this is going to do is I'm going to count some elements. I'm going to print out the beginning of a window. I'm going to run it. Oops. I missed something here.
No, it's seconds.
Well, see, give me a nice error message telling me what I messed up. Okay. Oops, I got another error. Okay, so I need to actually add a group by.
By tumble event times.
Oh, you're missing an N.
See, I should just copy and paste this instead of trying to type it. And I'll start doing that in a minute here.
Second.
And see, I just keep making syntax errors, and at least there's an interactive SQL shell. If I was doing this in Java, I would be easily 10 minutes in before I figured out, oh, I made a syntax error, or oops, I messed up the schema. Have to compile a program, have to run it. It takes a while. Okay. Great. So now we've got these 3-second windows. I've got 6 of them. It took a while to run because, well, that's about, if you take 3 seconds multiplied by 6, it's probably about how long we took. But you can see that I have every 3-second window, I have about 15 events. And so this nice interactive shell, SQL line, it's based on SQL line, lets you quickly develop SQL queries and experiment with them to actually, you can actually do things without writing Java code. So an example here is, let's say I have some data that I want to join with this sequence generator. I'm going to just copy and paste here. Let's see, so I don't have to make any more typos. Not tempt. Okay, so I have this CSV file. That looks sort of like this. It's some cryptic data. But what I'm doing here is I'm joining onto that window, or onto that sequence generator, some data. And what that data represents is your S is just a sequence number. Team is a team identifier, and points are points. So actually, what I've put here in this data file is sort of a simulation of a college football game, because, well, it's college football season, so why not? And so, at this point in the game, the one team scored 7 points. At this point in the game, the other team scored some points. And so we can put this into a window. This is a really contrived example, but it gives you some ideas. So now I'm going to take a window, and 12 seconds happens to represent in my simulation what the length of a football game is. And so I want to figure out the score of each team at the end of this football game. So it's going to read in my CSV file. And I'm joining it against the stream generator here, so I don't have to go and write a bunch of Java code to turn my simulated football game into something that came in a stream. I'm sort of using this as just a mechanism to mock out the data. But there's a nice demo in the last talk of Pablo actually building a extension of this stream generator that you can feed your simulated data directly into the SQL shell. And so if you've got like a data set that you want to mock up and run local queries against, you can do that. You could, in practice, run this against your live data stream as well. Again, I don't want to do that here. And so I've got one more piece of data I'm going to add. So I can enrich this here with another file I have that actually gives you what the teams are. So if I do a select star from info, okay, I have some random universities, their mascots, whatever. I can write a little bit more complicated SQL query and then join this static data onto my stream. And instead of getting out this sort of cryptic table of scores, I should get out something that's more interesting. Oh, there we go. So there you go. SQL shell is a pretty straightforward way to test, mock-up. And so these data sources that I used here are all local files, but if you can create external tables that are referencing BigQuery, PubSub, Kafka, a whole bunch of sources, and I'll get into that later in the talk. This SQL shell is not just limited to local data sources. Flip back to my slides. I can figure out how to get the slides back. Okay. Any questions on that?
Can you use different runners with the SQL shell?
Yes. I don't have any runners on my class path at the moment, but there's a set runners equals data flow. I don't have data flow in my class path, but if I did, this will give me an error that my only available runner is the direct runner. But if I had more runners in my class path, you just have to, add the jars to your class path. So if I downloaded the jars for the data flow runner, the Flink runner, and stuck them in this folder and set my class path when I started Java to be this folder, it would just work. There's also in Beam, I think it's called SQL, there's a shell folder, and there's actually a tool in there to build an Uber jar that has both SQL and one or more runners and a bunch of IOs. So we have tools for that. One of the other things we built, and this is my vendor pitch. I'll be really quick on this, but Google has taken this same SQL. We didn't actually use the shell, but we used the SQL transform hook, which I'll talk about in a couple minutes. We have this UI where you can write SQL queries. You can hit execute, and it will give you the option to spit your results out into a BigQuery table. And then you can hit launch, and it will launch a Dataflow job. And so in the Dataflow UI, it looks sort of like this. It's the same underlying SQL engine. It's still based on Beam SQL. But you can write a SQL job without even downloading a jar and launching it in your shell with through the Google Cloud. So maybe some other vendors will add things like that. Okay, now I'm going to talk a bit more about how this actually works. And so, really, what Beam SQL is it's actually, there's not that much code in Beam SQL if you look at our code base. It turns out it's really just Apache Calcite. Calcite handles our parsing, our validation, and I've put some stars at the end of here, which are new in this talk, and we'll get to that in a minute. It converts our parse SQL to relational algebra. It converts that physical, or the relational algebra to a physical execution plan using rules that we've written. So there's a Calcite optimizer that takes that logical plan that it generated, applies our rules, and converts it to a physical plan. It provides the JDBC driver that powered that shell. And it provides a whole bunch of built-in SQL operators and a code generator that actually provides the Java implementation under those operators. So, to give you sort of a block diagram of what this looks like, you write some SQL in Java. You can feed it into our SQL transform, which is just a transform that you can stick in any Beam pipeline. It calls into Calcite, which parses, validates, converts to a logical plan, converts to a physical plan, and spits out a pipeline. And so most of the heavy lifting happens in Calcite. We've just provided some rules on how to translate a logical plan into a physical plan, and then how to convert that physical plan into a Beam pipeline. But it's actually, if you look at the code base, it's a very small layer on top of Calcite. So the JDBC path is pretty similar. The SQL actually goes straight into Calcite. Beam isn't even involved until pretty close to the end of this. We have effectively Calcite spits out a physical plan that has our enumerable converter rule on the end, which converts your physical plan that's in the Beam type to the enumerable type in Calcite, which allows it to effectively the output of that type is a Java enumerable, which can then be output to the JDBC driver. So again, almost all Calcite involved. We do have this new version that's Zeta SQL. And this is what actually powers that Dataflow UI. And I'll talk more about what Zeta SQL is a couple slides later. But It's the same general idea, except we've replaced Calcite for parsing and validating with Zeta SQL. There's a piece in Beam that converts it to a logical plan. That gets passed back into Calcite, which actually does the optimization and the physical plan the exact same way as it would if you used normal Beam SQL. So for the normal Beam SQL path of parsing, validation, Calcite handles basically all of this. Yeah.
So I have a question for the runtime data structure for record.
Yeah.
And what kind of data structure you use for the record in the runtime?
So the records are Beam schemas that SQL will take in anything that is a Beam schema type. And so Beam schema now has all sorts of mechanisms for auto-detecting the underlying data types. If you have like a proto, an avro, pojos, you just have to apply the default Beam schema type detector to your P collection, and then you can pass it into SQL, and SQL will be able to inspect the schemas and read in your data types. The output of Beam SQL is a schema plus a row type, and the underlying data structure on a row type is just an array. So we output an array of object.
And the code gen for the filter for project, you do code gen for filter project, and then that code gen can be aware of the...
Yeah, I'll talk about that in like 3 slides. So if you still have questions when we get to the code gen slide, feel free to ask. But yeah, where was I? The output of Calcite's parsing is a set of high-level relational objects: filter, project, join, aggregate. There's 2 special ones, which are table scan and table modify, and those are actually how we get P collections into the SQL model through BeamIL source, or have a result P collection come out through BeamIL sync. Those are the 2 cases where we pass Beam specific types directly into Calcite at the beginning of the generation of the graph. So the graph sort of looks like this in the Calcite model. You write your SQL, you end up with a graph that looks like this. You have some tables. You maybe apply some filters, some projects. Do a join, whatever. That gets translated into the Beam model, which looks like this. This is one example of how this could be implemented. Your filter and projects are just Pardos. What was that one? Your join can become a cogroup by key. There's several different ways to implement that. And your aggregate becomes a combine. So there's a pretty much, one of the reasons this was so easy to do with Calcite is there's pretty much a one-to-one mapping from these primitives to existing Beam primitives. So Calcite applies a bunch of rules to optimize the plan. The biggest one is filters and projects are merged into a single calc rule, which is actually what gets fed into the code gen. Join gets converted to a Beam join, which is our own implementation of how to convert a join to whatever underlying Beam construct we want to use. Same thing with aggregate values. And then enumerable converter is that special case that wraps a Beam pipeline, runs it, returns the result as a Java array, an array of values.
And question for join.
Yep.
For join, where do you join? Do you know which side the table, which side the stream, which side bounded, and which side unbounded data set?
We know all that data, and so we have a cost-based optimization model, and that's about 3 slides away as well. that's actually really new that allows us to make some decisions on ordering of joins. I'll get to that in just a minute. Okay. So it turns out that Calcite is this really cool implementation of the Calc operator called Enumerable Calc that generates Java code to actually implement most filter and project operators that are interesting in SQL. So starting in Beam 210, we actually have a wrapper around that generates code for a Pardo instead of for iterating over an enumerable, and feeds that directly into a Beam graph. So we're using Calcite to generate Java code that is actually a Pardo, because there are a whole bunch of clean interfaces on top of this that we can take advantage of to hook how for example the values are read. Then Calcite generates code for calling functions or doing some manipulation on the data in Java, and then again there's a mechanism that we've hooked to allow us to return types that Beam can understand again. So this gave us pretty complete support for Calcite SQL operators. The code it generates looks something like this. It's actually not this clean. If you go and look at the code generator generates, the types are much more. It'll be much more cryptic code. But this is to give you an idea of approximately the Java code that comes out. So if you're doing like select ID, price, a couple different things, a filter. So your where clause, your filter, gets just converted into an if statement. We're going to read out that item, check to see if it's equal. That's pretty efficient in Java. For the price, we're just going to get the value, and then we're going to output a new row that contains your new data. Maybe we called your user-defined function that converts your price into some different currency. This all looks pretty much like Java code that you would write if you were writing the Pardo in Java. So there's unless you want to get super heavy into micro-optimizing your Pardos, it turns out that SQL will probably generate something just as efficient, or maybe even more efficient than what you would write from scratch by hand in Java. So if you were afraid to use Beam SQL for performance reasons, I wouldn't be, especially if you're doing simple things like this that would, a small SQL statement became a large chunk of Java code. So we support a bunch of different ways of getting your data into and out of SQL. The easiest one is if you have an existing Java pipeline, we can just pass P collections into SQL. And so that with the SQL transform operator that we have, you can apply that to your existing P collections. If you have a named set of P collections, you can select from those P collections using their names in SQL. But we also have a pluggable table provider interface, and this is what powers, for example, our SQL shell and the Dataflow SQL UI. And you can create data sources in SQL without writing any Java code. And so the ones we currently support are listed here. It's a pretty small set, but we hope to grow it. It's pretty straightforward to actually write one of these. All you have to do is write a wrapper around your I/O that, given a table name, can create the I/O. And so you have the ability to extend with a couple common things like the location of your underlying data source. You get a string that you can pass in. And then we have a table properties field that allows you to pass arbitrary metadata. So that's really the thing that you need to do to implement a new table source, is just wrap your I/O, parse out any I/O-specific metadata on how to either get to your data source or how to configure your data source. And then you can create new connections in pure SQL. We also have a pluggable metastore interface. And so this allows you to connect to external catalogs of data sources. So I think we currently support Hive hcatalog. I don't know if I haven't used it, so I don't know how well it works or whether it's complete. But I do know the Google Cloud Data Catalog connection works. And so if you have like your BigQuery and your pub subtopics defined in Cloud Data Catalog, you can hook up the SQL shell to that and use your existing schema definitions and table definitions in Beam SQL. And so I'm not going to spend too much time talking about this, but I mentioned it before. Beam Enumerable Converter is just a mechanism for wrapping pipelines into a format that spits out a object array that can be fed into a SQL shell. It only works in the direct runner today, and that's because we've taken advantage of everything running in the same Java process, and we've made some global state hacks to make this work. We haven't gotten around to handling streaming output or hooking it up to other runners, but certainly we are welcome to accepting contributions, such that if you have like a Flink pipeline, we could potentially take your output and stream it into a SQL shell. The interfaces support it. We just need someone to actually write the adapter to do that. If you're in the SQL shell and you do a insert query, so this would be insert into some output table, select from, and then the rest of your SQL query. We can run that in the SQL shell on any runner. And there's just a set command that I demoed as part of the demo at the very end there. So you can specify, say, I want to run in the Flink runner, I want to run some SQL, and it will work from our SQL shell. These limitations, of course, don't apply if you're putting it in a SQL transform, because it doesn't go through this path. So if you're putting it in an existing Java pipeline, it's really easy. So one of the new things that we have is Zeta SQL. And if you're wondering what this is the BigQuery standard SQL syntax. So how many of you are Google BigQuery customers? Just wondering. Yeah, okay, so about half the room. The reason we've added this is because we found a lot of people are already using BigQuery to write SQL, and they're writing, for example, batch jobs that are actually micro batch jobs that would be better suited as streaming jobs. And so one of our goals here is to make it really easy for you to take those jobs and copy them into Beam SQL and change as little as possible and have something that works. It's not there yet, but certainly we want some feedback. It's written in C++ as well. And that's the underlying Zeta SQL library. The adapter in Beam is in Java, but the C++ code for the underlying parser is still there. Only runs in Linux. Sorry if you're developing on a Mac. We're working on it. It doesn't replace Calcite. That's an important part. We certainly would like to contribute some of this back to Calcite. We don't have time for that at the moment. And there'll be a long discussion on what's valuable and what's not. At very least, we're going to improve some of the BigQuery parsing in Calcite at some point, so we can have a pure Java path that at least some of this works in. So the other thing that we just added, this was an intern project at Google, really cool, is cost-based optimization. So your data sources can indicate to SQL that they have either a row count for batch. So if you're selecting from BigQuery, we can tell you how many results are going to come out of that table and feed that into the optimizer. Or if you're from Kafka, we support feeding in the rate of data coming in that stream, the rate of messages coming in on that stream. And so when we have those, we can actually pass that data into the Calcite optimizer. It can then use that to reorder joins such that you're joining in the most efficient way possible. You want to join the least amount of times that you possibly need to. So for example, if you have a a couple small batch sources that you're joining. You can join those once and then join them on the stream instead of taking the stream and then joining batch source 1 and then joining batch source 2 onto that stream. And so primarily what this powers at the moment is reordering joins for the most efficient execution. There are certainly other things that can benefit from it. We just haven't had time to build those cases. So pretty much done here. The biggest thing we have left to build is more I/O connectors. We're certainly taking contributions on those. There are a couple more places where code generation might help us. I think we're pretty much done on that front, though. Right now, there's someone who's actually just going to start working on project and filter pushdown, and this is really cool. If your data currently exists in a database that itself can run SQL or at least some filters and project operations, we want to be able to take those and run them directly on the database. So if you're doing something like selecting from BigQuery and joining to something else, you might have a big BigQuery table that contains columns that you aren't going to use in your join. And so right now we dump the entire BigQuery table. We do the filters in Beam, and then we do the join in Beam. And really we can take those filters and say, well, just send us the data that we care about later in the pipeline.
But that shouldn't be part solely on the SQL part, because it's schema-aware P collections on the whole chain should be aware of those things as well. If you don't take SQL into account.
So long term, we want to make it a higher level construct in Beam, right? There's probably value in having like a whole pipeline optimizer in Beam that can take advantage of the schema knowledge. Potentially, we also have the problem of if you have multiple SQL transforms in your pipeline, we optimize each one separately. And you probably, if they're back-to-back, they can potentially be merged and further optimized. So we're starting here because we already have all the metadata in a great format for manipulating it. We certainly have opportunities to push that higher, or I don't know which direction it is, lower down the stack. And yeah, that's already come up several times to the people I've talked to about this. It would be great if we had a whole pipeline optimizer. We also have there's a bunch of SQL or a schema operators that look like SQL but aren't SQL. And so if you intermix those in SQL, we should also be able to optimize that. And currently, those operators have no optimization. So an advantage of using SQL over those is that you do get them run through a SQL optimizer. One of the other difficulties we have is what is a streaming join? So joining across windows, it turns out, is a difficult problem. Does anyone have use cases that do this? Yeah, okay, at least one. So I want to talk to you later.
Actually, I have a code jam to generate the Beam code from Calcite plan. I have a talk tomorrow on that, so we have a similar problem.
Okay.
Yeah. Let's talk.
Let's talk afterwards. So one of the other things we want to take advantage of is the Portability Framework. So what we have right now is this. This is the portable part of Beam SQL. So you can write SQL, write it on top of Beam, and it will run on all of these different engines. So you have a single SQL dialect that you can run on Flink, Spark, and so some of these systems have their own underlying SQL layer that can actually do better optimization than we can if they have knowledge of what your SQL query is. So we'd like to add some of that metadata to the portability layer. So for example, if you're writing a Beam SQL query and you're running it on Flink, Flink can say, well, okay, that's SQL. I know SQL, and take your SQL query, turn it back into a raw SQL string, pass that into the Flink SQL engine, and potentially do better runner-specific optimizations than Beam could. The other thing we'd like to do, and there was an earlier talk about this I saw today, is make SQL available from languages other than Java. So this is via the expansion service. I think there's a demo of it that I heard was floating around. But potentially you should be able to write SQL, stick it in your Python pipeline, and have it turn into Java SQL under the hood without you having to write any Java code. And so this is really powerful because potentially things that you write in SQL in your Python pipeline will be more performant than just writing the same thing in Python. It also gives you a much simpler interface to doing some of these basic operations that potentially could be a bit of code. Okay. Any more questions? How am I doing on time? I think I'm 10 minutes over.
Yeah, you have 9 minutes.
I have 9 minutes left.
Yeah.
Oh, I'm not 10 minutes over. My timer says I'm at 52 minutes, so
Or maybe, yeah.
maybe I'm 10 minutes over. Oops. I told you it was going to be 2 hours. Okay, well, if you have any more questions, feel free to come and bother me. I'll be here all day tomorrow.